Okay, my Algebra 1 friends, welcome to Remote Learning 6. And today we are going to rather significantly change what we've been doing. So, we have been doing a lot of factoring, all sorts of factoring. Factoring using the greatest common factor method that I call old school. We've been factoring trinomials by playing think of two numbers if it starts with a 1. We've been factoring trinomials by using the Xbox method. And we do that when the leading coefficient is not a 1. And we have been factoring by using the difference of two squares pattern. That's a unique pattern where there's a minus sign and only two items, both of which happen to be perfect squares, thus difference of two squares. We've been factoring completely by using combinations of methods. And we have factored by grouping when there are 4 items. Sometimes you got to do a little rearranging, but you grab the first 2 terms and factor out what you can, and the last 2 terms and factor out what you can, and cross your fingers and hope that there is matching binomial that can be then factored out further. Okay, so rattling all those things off, that's what we've been up to. It's not necessarily going to go away, but we are moving past factoring as like the main idea of the lesson. Okay, so why did we factor? And the answer to that is we need to factor to turn polynomials into a multiplication problem so that we can solve them. The solving technique was to use the zero product rule. And it's easy to make them equal to 0, ship everything over to one side, but it's less easy to turn it into a product. That required all those factoring things that I rattled off. Okay, so solving and factoring are not going away, but the theme of the lesson is changing here. Okay, so we're going to be graphing. And we've graphed lines before on the Rene Descartes Cartesian plane, on the Cartesian plane, the XY grid system. And we're going to be graphing on that grid system again, but we're not going to be graphing lines. We're not going to be graphing linear functions. We're going to be graphing these new functions, which are called quadratic functions. And you already know what a quadratic is, although you may not know that you know it. Okay, so let me give you an example of a quadratic equation. Okay, so here's a quadratic equation. X squared minus 7x plus 10 equals 0. So it's an equation because it's got an equal sign, and it's quadratic because it's written as this particular trinomial where it goes x squared, x, and then a constant. Okay, so let me say a little bit to that because people think quadratic, or if they think about just like the word, then quad means 4. And so, what the heck? There's only 3 pieces. There's only a squared. There's not 4 of anything. Like, why on earth are they called quadratics? That's so, like, weird. Okay, so I'll speak to that just real quickly. So, quad does mean 4. And then, what's a shape with 4 sides? Yeah, so everyone would say square, or maybe you would say rectangle. But if I could get you to think of a square has 4 sides. Okay, and in Latin, the idea of squaring, this idea of squaring has the name quadrantum. Okay, so because it has a square has four sides. So in Latin, the idea of squaring is this sort of prefix having to do with the square. Okay, so we would maybe call it like we'd simply call it like a squared equation, but those that would speak Latin would call it a squared equation, but their word for squared is quadrantum. Okay, so that's sort of the history of it, and that's why it's still called a quadratic. What you need to realize is that a quadratic equation is an equation where the highest power is squared. So a quadratic equation can have all three of these pieces. It could be missing this or missing that, or missing this one and having that one, but it has to have the x squared for it to be a quadratic equation. And for it to be a quadratic function, it's also going to have an x squared term in it. Not an x cubed or an x to the fourth. It's going to have x squared as its biggest, and then it may or may not have these other pieces. Okay, so since I have this quadratic equation, the squared equation over there, I can solve it. Okay, so does it equal 0? Check. Is it factored? No. Think of two numbers game. And then, excuse me. Okay, I think I'm good. Now that it's written as a product, I can use the zero product rule, which says for me to break it apart into its two little packets, and I get these two small equations, both of which are easy to solve. Okay, so that's a repeat of using the zero product rule. The point was, why is it called a quadratic equation? Because it's got a squared. Okay, makes sense if you're Latin. If you're a Latin speaker, I suppose. Okay, so a quadratic function is something that looks like this. Okay, so they have an output that is obtained by putting an input in for the x and computing. So A, B, and C are numbers. Okay, so like 1, -7, and 10. So that'd be like a 1, -7, and 10. Okay, x is the input, and y is the output. So if we were going to go all Rene Descartes, we would have an equation where there would be numbers in the A, B, and C spots, and we'd put in a number for x and compute, see what came out. Pair them up. Put in another number for x, compute, see what came out. Pair them up, and do that, and do that, and do that, like Rene Descartes did, until such time as we were able to go to the grid system and plot all those XY combos and see what sort of shape showed up. Okay, so that's the idea. We're moving past quadratic equations for the moment and moving into quadratic functions, and particularly we're going to be graphing quadratic functions and seeing what shape emerges. Okay, so hopefully you recall that back when we were graphing lines, we would use x as the input and y as the output, and we had our rather famous y equals mx plus b. But as we became more and more proficient at playing this game of graphing the lines, I introduced you to a second notation, which is called function notation. And it is back. So function notation names the function, reminds you what the input variable is, and then expresses what the function does over here. Okay, so here everything is the same. A, B, and C are still just some numbers, and X is the input, but this time f at x is the output. Okay, so let's play around with a very basic quadratic function. So let's graph the most basic quadratic function that there is. Okay, it's called the parent function. Well, I suppose there's a lot of parent functions. This is the parent quadratic function. There are a lot of function types, like there's a line and a quadratic and a third order and a fourth order, and there are all sorts of function types, and they each have a parent function. That is to say, they have the original version, the most basic version. Okay, so in this case, I'm going to rewrite my directions more basically as graph f at x equals x squared. Okay, so what this means is that a is 1, b is 0, and c is 0. So I sort of killed off the x part and the constant part, and I put a 1 out front. So like I said, I'm making like the most basic quadratic function that I could possibly make. And we're going to graph it. Okay, so here we go. Let's build our table. Try not to worry. I'm not going to have you make too many of these T tables, but let's do it. Let's do what we've sort of done in the past and put in 5 numbers, and then we'll very carefully see what comes out. Okay, so let's see. What happens when you take -2, notice my parentheses, and square it? That is to say, you multiply it by itself. All right, so then we get 4. And when we put -1 into the machine, -1 gets squared, but make sure you put the parentheses, otherwise the calculator would give you -1 when the answer is really +1. -1 times itself. Okay, well, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. I can do lots of these. I'm going to put in -3. Oh, -3 squared is also 9.
Sorry, I forgot, darn it.
Okay, so let's move towards graphing this x squared function and see what we see. All right, I just set in a scale. I'm going to count by ones, but I don't want, that's not -2. I don't want it to be too crowded with numbers everywhere, so I'm only writing every other one. Okay, and yeah, so that's the origin right there, 0, 0. Well, let's see, -2, 4. So that's left 2, up 4. I'm going to switch colors for the plots. -2, 4. Bam. -1, 1. 0, 0. 1, 1. 2, 4. 3, 9. I'm not going to do 4, 16. It's way up there. And then I do have -3, 9. Okay, so first and foremost, I just want you to observe that this is not like a V. These don't line up, these points over there. So we don't get a big old V. We do, however, get symmetry. Like this point gets folded over the y-axis to that one, and that one gets folded over there, and this one gets folded over there, and this one gets folded over and lands on itself. Okay, so yeah, I'm sure that you are way ahead of me and you know what this thing is, but oh, that didn't work out. That one was pretty good. Oh, I'm gonna have to redo them both. I should have erased it. Well, I did it. Okay, let's make this one a little bit better. Goes. Okay, so that is pretty good drawing. And that is our parent function for the quadratic. This shape is a parabola. It's got some pretty interesting characteristics, like it gets steep fast, but I will say that it gets wider and wider and wider and wider forever and ever, and it never goes like vertical, never goes straight up. Okay, it starts to look like it goes straight up, even over here at like 3, 4, but no, it just keeps on going. There are values that get higher and higher, like you put in 5 and you're up at 25, and you put in 6 and you're up at 36, but you put in 7 and you're up at 49. So it just keeps, as I move over, it keeps getting higher and higher, but it does reach them. Like it doesn't reach like 8 and then it can't go past 8 because it went vertical, right? It definitely just keeps getting wider. Put in 10, you're up at 100. Okay, likewise over here, there's all of those. Put in -5, you're up at 25. Put in -6, you're up at 36. So the parabola gets wider and 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 higher and higher. Okay, but the parent function never goes down below. As low as it ever goes is here at 0, 0. All right, so I need to bring in some vocabulary words, and they will enable us to sort of understand directions as we progress. So let's talk about this point. All right, there, that has a name, and it's called the vertex. Those are E's. Okay, and the vertex on this one is 0, 0. It is not always 0, 0, but in this case, the vertex is at 0, 0. Okay, so then let's also talk about how on this side of the function, so all of this over here, from 0 going, we call this increasing. And the idea is that as you put in a number, it gets higher. As you put in the next number, it gets higher than the previous number. As you put in the next number, it gets higher than the previous number. Okay, but over on this side, things are decreasing. There's like moving down towards the vertex. Okay, so that means like, that's -3, we're up there at 9. But then when I put in the next number, which is -2, it moved down to 4. Put in the next number, it moved down to 1. Put in the next number, it moved down to 0. And then over here, it starts moving back up. So you've got a decreasing leg of the parabola and an increasing leg of the parabola. Right? And those are just some vocabulary words that we need you to be aware of. Okay, so let's see. I think I'll get a little fancy here and do this move. And let's see, I'm pretty sure I can change the properties of this. Ooh, nice one. Oh, so now I just made it all dashed. Okay, and I'm doing that for a reason. I just want this to be known. I was going to do it in black, so let me do it in black. Come on. This line is called the axis of symmetry. It's the line you fold over, and then the legs of the parabola land on one another. So this point folds over to that one, but then this point folds over to that one. They all do. And likewise, this one folds over there. Okay, so this is the line that the parabola is folded over, and it's called the axis of symmetry. The equation for this one is x equals 0. So if you have your notebooks from first semester, like we had dog-eared page of the vertical and the horizontal lines, and this is the vertical line, x equals 0. It means that you always go over nothing. You go to the right or left 0, but then you go up some amount, and you get all the points that make up that line. Okay. I'm going to roll into the first example, and in so doing, we will be able to talk about some of these ideas as well as understanding the directions. Okay, so let's consider the graph of the quadratic function, and then here is the graph. All right, so using the graph, you can identify the characteristics such as the vertex. So there's the vertex, and it's at left 1 down 2. So here's 0, 0, to left 1 down 2. We can identify the axis of symmetry. So again, it's dashed. This time it's not the y-axis. So you have to figure out where it is. And it's always left 1 up something or left 1 down something. So here's that left 1. Always x is -1. That's the equation for the dash line. Okay, and you can also talk about the end behavior of a graph. Okay, so I didn't mention it in terms of like that language, but the end behavior is what's going on when you think about moving to the right or moving to the left. So the ends, like the left hand end and the right hand end. Okay, so let's lay that one out a little bit. Okay, so I like to think about it like this, and then I'll show you what the book does. Okay, so as, that's not an S, as the input goes way, 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 way out to the right. Okay, as the input goes to infinity. So as I go out here, the function, the graph, goes higher and higher and higher and higher and higher and higher. Okay, so as I move to the right, the function goes up. That's the end behavior. Out here, it goes up. Okay. Also, as x goes to negative infinity. So as the inputs become more and more negative, like as you put in -4 and -6 and -8 and -1,000, as you move way, 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 way out here to the left, the function goes up and up and up and up also. So this one would be as x goes to the left, the function goes up. Okay, that's in behavior. It's just describing what happens way off to the right and or way off to the left. Okay, so then I'm going to introduce a new topic while we're over here. It's not a new topic, but it's maybe like a topic we haven't talked about for a little while. That's going to come into play. And that's sort of our old words domain and range. Okay, so domain is a collection of all of the inputs. All right, so then it's a list of the inputs. This is a list of all of the outputs. And they're big lists. If you think about what you can put in, well, you could put in -1 and you get out -2. But you can put in 0 and you get out -1, it looks like. And you can put in 1 and it looks like you get out 2. And you can put in any number. You can put in a half and it looks like you get out 0. But you can put in 5.5, which is off my space, and you get something up there because the parabola gets wider. But like you can put in positive numbers, you can put in negative numbers, you can put in 0, like it's all of these values. And for every input, there is an output. It might be like super high up there, or like for these, maybe it's down a little bit, but inputs, you can put in anything. Okay, so the domain is all real numbers. We are not limited. We can put anything we want in. But the outputs never get lower than this value right here, which is -2. There's no -3 output. There's no input that brings you as low as -3. There's an input that gets you as low as you ever get, which is -2. Okay, so the outputs are -2, -1, 0, of course the fractions in between, but -2 and above. Okay, so then we need to come up with a way of writing that. Okay, so then I can have you just write like this. You might say something like all numbers greater than or equal to -2. Or if you want to get fancy, you just write y colon y is greater than or equal to -2. And we're supposed to put it in these fancy little brackets. Okay, so that's the fancy version, and then I'll go ahead and introduce you to this notation here, but it's that little colon is the phrase such that. So this reads like this. The outputs such that the outputs are greater than or equal to -2. And that describes what I just described right here. Okay, and then while I'm at it, if you want to get super fancy up here, you write the inputs such that the inputs are members of the real numbers. And then that's getting super fancy. Okay, but you don't need to do my crazy bracket stuff. So we're about a half hour in, and I would like you to do a few problems. So this is the assignment part 1, and I've gone ahead and brought the images over to the video So I can point to a few things, but I need you to, go to your textbook and look at these drawings. And I think I'm going to ask you to redraw them. Okay, so make my directions clear. I want you to draw each parabola on a piece of graph paper and then identify these characteristics. And that's going to be this list over here. Okay, so I want you to make sure that you label and draw the vertex, including its coordinate. Okay, then you should get a ruler and draw a dashed line and label the axis of symmetry. I'm going to abbreviate that. Okay, including the x equals value. I'll put question marks for all these things you need to fill out. Okay, and then you can draw like a little arrow system where the parabola is increasing. I did that in red, and then you can draw on it where the parabola is decreasing. No, that's not true. I did this one in green and this one in red. Okay, and let's see what else. Oh, that's right. Do the end behavior. And finally, the domain and range of each. Okay, so that's a lot of characteristics, but I think you'll find that there's a pattern that goes with this, and they're just the 4 problems. Okay, so by identify characteristics, this is what I'm asking you to do. It starts with the drawing. Okay, thanks a lot. I'll be back for part 2 in a few minutes.